8, Unit 5 Functions, Lesson 8, Recognizing Linearity. I want you to consider these two situations. We've got someone parachuting to the ground and a bowling ball falling to the ground. Which one do you think is going to be linear or nonlinear? And then we'll go ahead and graph them and compare. A linear relationship is going to always have the same slope, and that's kind of how we are able to tell. So I need to scroll this so that I can see the table and go ahead and do the graph. The parachute at 0 seconds is at 300, I don't know, is that feet? Yeah, it's feet. And then at 1 second, it's at 285. 2 seconds at 270, 355, and 340. That actually does look linear. All those dots are in a nice straight line. It went down 15 feet every second. Now let's look at the bowling ball. The bowling ball starts at the same height, 300 feet. After 1 second, it's gone slightly further at 284. After 2 seconds, it's at 236, a tiny bit less than 240. Then it goes to 156 after 3 seconds. Let's see, this is 156, slightly above 150. After 4 seconds, it's cleared down to 44. It's going to be about right there. And this one we can see is not linear. The longer the bowling ball falls, it tends to fall more quickly. So you can also see it's just not linear. And there's a reason for this. The parachute, the reason it's linear is because of something called terminal velocity. The big parachute catches a lot of air and increases the drag. And the acceleration due to gravity and the resistance due to the drag force cancel each other out, and it just stays at the same speed. Now, eventually, the bowling ball could get to its terminal velocity and stop speeding up, but it's got a much higher terminal velocity than the parachute will. Now, let's go right down. Okay, to tell whether a function is linear from a table, you just want to check the slopes. And this first one is linear because the slope for the first part is negative 8/3. For the second part is negative 8/3. And for the third part it's negative 8/3. If the slope remains the same, then it is linear. If the slope changes, then it's not linear. And this time on the second example, the slope goes from 9/2 to 22/2 to 55/2. And those are not the same, so it's non-linear. On a graph, it's probably the easiest to tell. Linear and non-linear. If it's non-linear, it's because it's not a line, it curves. And if it is linear, it is a line. Linear is just your adjective that means like a line. From an equation, if an equation is going to be linear, it needs to be of the form y equals mx plus b, or be able to be solved into that form. This first one just has a slope of 0 and an intercept of 4.7. It's completely fine. It's linear. This second one has a slope of pi and an intercept of 0. It's linear. This one with an x on bottom, that cannot be written in the y equals mx plus b form. That's actually the one that's not linear. This last one, if you distribute it, you'll find the slope is 4 and the intercept is negative 4, which I think is what... I've even got a graph of that. I forgot down here. The way y equals 4x looks when you graph it is it gives you this shape called a hyperbola. But you can see from the graph there it's definitely not a straight line. Okay, we've also got simple interest and compound interest. You learned about simple interest in 7th grade. It's I equals PRT. But it's just based on the original balance. You can see with this 10% interest, it just adds $10 every year, and that's linear. Now, compound interest adds 10% every year, which the first year is $10. The second year, it's actually $11 because 10% of $110 is 11. Then it adds $12.10, then $13.31. Then it will add $14.64. So that would not be linear at that point. All right, here's how do you tell if something's linear? These are the notes. I can determine linearity from functions in multiple representations. In an equation, you just want y equals mx plus b. The input variable, x, is multiplied by the slope. That's what you're looking for. If it's multiplied by something else, or if it's got an exponent on it, then it's not going to be linear. In a table, the rate of change remains the same for every pair of ordered pairs. In a graph, you're just looking for a straight line. In a situation, the rate of change is going to remain the same across the domain of the function. Okay, looking at a few quick examples here. Do each of these represent a linear function? Now this first one, it is linear, and if you were to solve it for y, you would get y equals negative 2/3 x plus 7/3. So it can be solved into y equals mx plus b form, to a slope-intercept form. This second one is linear as well. If you subtract x from both sides, you'll have y equals 3x plus 5. So we got a slope of 3, intercept of 5. This last one is not linear because of the x squared. X is being divided, which doesn't happen in y equals mx plus b. And it's got an exponent on it. The next one down, this is not linear because of the square. This one is linear. It's just got a slope of 1/3. This one's linear because you can just distribute it, and then you get 2x minus 8. That's completely okay. This one is not linear because if you do distribute it, you get x squared plus 2x, and x squared is not a linear term. This one is not linear because of the x on the bottom. This one's fine. 8 is the intercept, 2 is the slope. This next one is no because you're square rooting the input term. The next one is yes because 873 is the slope, 1045 is the intercept. And this last one is no because of the cube. Let's see if this table shows a linear relationship. If you're checking a table for linearity, you need to check every single change and make sure the rate of change remains the same. So I'm checking the changes along here. And the changes are not the same, but that doesn't mean it's not linear. We need to look at the rate of change. Getting from 23 to 8 is subtracting how much? 15. Getting from 8 to 3 is subtracting 5. Getting from 3 to negative 2 is subtracting 5. And getting from negative 2 to negative 22 is subtracting 20. Now let's compare these as slopes. Negative 15 ninths, negative 5 thirds, negative 5 thirds, and negative 20 twelfths. Now those two in the middle are the same. The first one's actually the same too. If we just divide top and bottom by 3, reducing that fraction, it's negative 5 thirds. And if we divide top and bottom by 4, reducing that last fraction, it's also negative 5 thirds. So since these are all the same slope, this table has a linear function in it. Okay. All right, for the sunflower seeds, what's the missing value to make, well, the table shows the cost, y in dollars, of x pounds of sunflower seeds. What is the missing y value that makes the table represent a linear function? Well, as you can see here, if we go up 1 each time, that's actually right in the middle. Instead of going up the full length, we only need to go half as much. So this would go up 2.8, but we only need to go up half as much, so we need to add 1.4 to that. So 2.8 and 1.4 is 4.2. So the missing value in the table is 4.2. B, write a linear function that represents the cost y of x pounds of seeds. Well, I think we already found the slope. 2.8 over 2 is 1.4. The y-intercept, we'll go ahead and find it using our backup method. We just need to plug one of the points in. Let's do $2.80 for 2 pounds. And 1.4 times 2 is 2.8. Oh, that's interesting. We subtract 2.8 from both sides, and we get b equals 0. So it's just y equals 1.4x plus 0, and that's it for finding the cost. I might put that as 1.40 because it's dealing with money. All right, the frequency of light. So the frequency y, measured in terahertz, of a light wave is a function of its wavelength, x, measured in nanometers. Does the table represent a linear or nonlinear function? Well, to determine linearity, we just need to see what happens as we move across here. Each time we take a look at the wavelength, it's 65 less than the one before. And that seems pretty good. We do need to check what's happening with the other ones. In this first step, it looks like we add 50. The next step, we're actually adding 62. And that's a bit of a problem. These are not the same. 50, 60 over negative 65 and 62 over negative 65 are not the same slope. We could continue checking, but we already know that these aren't the same. So it doesn't even need to, we don't even need to check the rest of them. The slope does change, so this is nonlinear because the slope changes. Okay, let's take a look at what you'll be doing in the practice. On number 1, you've got 6 problems, 3 graphs, 3 tables. Determine if they're linear or not. You just check to see if the slopes are the same on the tables. And the graph, you just look and see if it's a straight line. Number 2, are these linear from an equation? 3 is just a review of solving for x. 4 looks like function notation again. Number 5 is a modeling problem, and that looks familiar. Sunflower seeds. Oh, we talked about that earlier in this video. Number 6, solve by graphing. You'll need to graph both of those, see where they cross. Number 7, fill in the blanks so that this ends up being a linear function. And then tell me how you know it's linear. That's open-ended. And then number 8 is looking at a situation and deciding whether it's linear. You'll be able to tell if it's linear if the rate of change remains the same.